So I get to hype up Sander now before his talk. So all of this wouldn't be possible without Sander. It's why everybody on the Twitch stream is saying, "Oh my God, the audio is so good." As you can see, he also does parkour, running around, fixing everything. He's also up to like 2, 3 in the morning, pulling all the backups onto extra drives, etc. So Sander doesn't work as a programmer. Instead, he's a film sound person. But he also just programs because he's that awesome. He does many other things, kind of like Wasim. He's like a mirror Wasim figure, but he's not a doctor. He's something else. So, can we get a big round of applause for the guy who's making this all possible, Sander?
Thank you, guys. All right. Wow. It's an honor to be here after many ridiculous months of trying to get this thing to come together. It's awesome to see everyone here. And I'm going to try not to start this out by getting emotional, so let's talk about something technical. My talk is about dynamic phase alignment. I was considering going to the extra jargony title of dynamic time warping with spectral phase delta compensation, which would have been fun, but I didn't want to scare people. My actual job is being a production sound mixer, which means I chase actors around with microphones on film sets. And there's an issue that we encounter in post when we're done filming and we sit down to mix the audio. We'll have our actor, and I'll attach a microphone under the shirt, usually on someone's chest, and I'll hold a boom overhead. The boom sounds better than the lav in almost all cases. We say boom is king, because it's very natural to be listening to someone at about this distance. It's not very natural to be listening to someone from here. Right? You don't usually do that. However, when you start out with the boom track, you want to add just a little bit of the lavalier track, because it has a nice, warm, close feeling that feels very cinematic and epic. But the issue is that the distance from the sound source, the actor, up to the boom is much greater than the distance to the lavalier. And because the speed of sound is not infinite, you get what is called a TDoA, time difference of arrival, the most awkward acronym in all of sound. I don't know why it's not time, or like difference in the time of arrival, but no, time difference of arrival. Because you might think, take a sound wave, add sound wave, get more sound wave. But if you have two sound waves that are not aligned, you actually get less sound. Right? You get less output, you get destructive interference, because a -1 and a 1 become a 0. I'll give an example. Oh, wait, hold on. We can do a real example. We have mics. If you turn off my lavalier, I'll do green and blue. All right, let's see if this works. Hello, testing 1, 2 on green. Testing 1, 2 on blue. Okay. So I'll move these, and let's see if you can't hear the phase and destructive cancellation happening while I shh. Could you hear that? All right. So that's destructive interference, and it becomes an issue because you want to add the little bit of warmth from the lavalier track, but when you add it in, you often just lose all the little bit of warmth the boom already had, because it ends up destroying the signal. And so, let's see. Let's see. There it is. Yeah, this is usually a really easy problem to fix. It's super trivial, because all you have to do is try all the possible alignments until you find the one that has the most output. This is code you will write in 2 to 3 minutes. It's just like for all of them, try it, which one has the most output, that's the one you choose. Issue is, actors and microphones on set move. So the time difference of arrival changes. So you align one place, but then a second off, it's wrong again, and it's canceling. And so it's an infinite game of whack-a-mole where you try and move it, and then that goes out of phase again. So you have to sit around painstakingly, like stretching everything, and it's really obnoxious. So that's a no-go. So we need some way of like warping dynamically through time. luckily, there's an algorithm for this called dynamic time warping. And I've written a little program to show you how that works. Shout out, File Pilot. And also shout out to Odin and Raylib for making this very easy. So here are two very short audio files that we'll use as examples. We'll have a boom track and a lavalier track. What we want is to align the lavalier track with the boom track using dynamic time warping. So we're going to line them up like this so that we can create a grid. This is a grid of floats. And the first step is just coat the left edge and the bottom edge with infinities. And then we start in the bottom corner here. And we're going to look at the corresponding points. So point 1 and 0, figure out the difference between the two, which in this case is really simple. 0.10 is 0.1. You can have more complicated functions for doing this kind of thing if you have like multi-dimensional data you want to compare, or like video feeds. You can have a fancy function for figuring out one number for the difference between the two at that point. And here comes the magic of dynamic time warping, and the key to how it works is now we look at the 3 preceding cells and see which one is the smallest. In this case, pretty easy, 2 positive infinities and a 0. The 0 is the smallest. We store that direction. And then we add that 0 into the current cell we're working on. In this case, it's a 0, so it's not going to add anything. But if we look at this one, the difference here between the 0.5 and the 0 is 0.5. We're just doing absolute delta, super simple. Now we compare the 3 preceding, and the smallest of those is the 0.1, which we add into the 0.5 to get 0.6. You'll start to see the pattern here. We do that one, 0.1 versus 0 becomes 0.1. Smallest of the 3 preceding is 0.1. Add that in, get 0.2. Same thing here, 0.5, smallest is 0.1, we get 0.6. We keep doing this, and you can see how that wavefront moves. You can also probably imagine how you'd very easily parallelize this. Until we get to the top right corner, that's kind of a magic number that a lot of dynamic time warping research I've found is just really obsessed with that number, because it's in one floating number, representation of how similar these two waveforms are, kind of getting to ignore some timing differences, which is really useful if you're doing speech recognition or trying to compare recordings of weather patterns or something like this. And so in those cases, they're really interested in that number. I am not. So there is one neat trick you can do with it, which we can talk about later, but for now, we can just throw away the numbers. I care about the arrows. And this is going to be really familiar to the game dev people who have done some pathfinding, because we're just going to start at the top right, and we're going to follow the arrows down till we get to where we began. Now we don't need the arrows anymore. What you see here is the optimal warping path for mapping the lavalier track to the boom. And so if we look at the alignment here, this peak here of 0.5 aligns with the 0.4 peak over here, and the trough of -2 in the lavalier track aligns with a -1 in the boom track, and so on. And also, I just want you to record this pattern in your head, just how this looks. Where you have the cost map of the grid, just the colors, and then you have what will be a dark valley in the middle that you want to walk along for the lowest cost warping. So let's smush this away and make an output buffer. This will be the warped version of the lavalier track that'll fit with the boom track. We're going to start at the top right with the arrows again. First thing we output is the 0 from the lavalier track to the lava-warp track. Those align, great. We move down a step. This is called a deletion, because the 0.1 towards the very end of the lavalier track is not going to be output. That's deleted because we've already put a 0 there. We do a diagonal, Now we output the 3 from that peak, because that aligns with the 0.4 peak of the boom track. And we keep moving along like this till we get here. Now we're doing insertions when we move to the left. There are 3 zeros here in this little break between the trough and the valley here, or rather the peak. Whereas in the lavalier track, there's only 1 0. That's why it's doing insertions. It's inserting the same 0 3 times along here to match it. And then we go into the valley or the trough to match there. We start climbing up to match the peak, and we insert the final sample, delete the 2 zeros at the end, and there we have an aligned version of the lavalier track. Let's have a listen to what this sounds like. Let's see here. First, I got to introduce you to the test audio we're doing. What I did with the microphones there, this is a recording of me doing the same thing, but I'm saying testing 1, 2, 3, just going like this. And those 2 microphones are mixed together. You'll hear the problems, hopefully.
Testing 1, 2, 3, 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 1, 1, 1, 2, 2, 2, 3, 3, 3, 3.
All right. And now you're going to get to hear the naive warping just using that algorithm. Now you're only going to hear the track that's moving after it's been attempted to warp to the one that's static.
Testing 1, 2, 3, 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 1, 1, 1, 2, 2, 2, 3, 3, 3, 3.
Yeah, it's not great. Not very usable. And the reason why this is happening is, let's go full screen here. There. Yeah, I'm charging, good. The reason why this is happening is because we're offering the algorithm a chance to change the alignment at every single sample of audio. And so, you let it just adjust as much as it wants, every single sample, that's 48,000 times a second, you're gonna hear that as distortion. And so what we can do is if we look at this path, we look at just the insertions and the matches, those are the things that create more output, and we look at those as offsets from a center line, then we can output that as just a series of offsets, an offset series. That's just an array of floats. This is ripe for smoothing. So we can smooth it out, right? We'll get rid of all that jaggedy movement. Let's hear what that sounds like. It'll sound better at first.
Testing 1, 2, 3, 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 1, 1, 1, 2, 2, 2, 3, 3, 3, 3.
We're not quite at cinema quality yet, but we're getting there, all right? Let's see. So this offset series thing is really useful for debugging because you can just output it as a sound file and open it to look at it. So let's look at the first wave that we had. Here you can really see why this is distortion, right? Because it's going crazy. It's really eager to change the warping, to just minimize the cost at as much as it can. But if you kind of squint your eyes, you can sort of see it goes up and then down and then up and then down. That is my hand moving like this, away and closer. And then we can look at the smoothed version. Yeah, you see the trend, but you also see why that was really goofy towards the end. And what that is that my voice is cyclical. Well, it's not unique to me. I hope your voices are also cyclical and speak in frequencies, which means that there is a cycle that you can align to, but that also repeats, right? So you can be off by a cycle, and that'll mostly be in alignment. And so the algorithm is really eager to just go, if that will reduce the cost. And so it'll be off by multiple cycles and then go back. It looks something like this in the cost map, where you can see the path is going along just good, but then it gets kind of confused and figures out, I could align over here too. And us as intuitive humans with brains can go, silly algorithm, you should have gone there. But how do we make it do that, right? And there's an evolution of dynamic time warping, or a mod you can make, called immersing, which is very simple and helps solve this problem. You take anything that's not a match, that is to say, anything that's not a diagonal, you add a small cost. And that makes it so it's not feasible to go off, 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 back, 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 and then pay a penalty for moving back to where you already were. So it's going to stay in its lane for a little bit longer. Here you can see the results of that. More immersing, less noise, more solid signal. So as a, as a reminder of where we started to where we are after immersing and smoothing, we have this. That's my arm moving, and basically nothing else. So let's listen to what that sounds like.
Testing 1 2 3, 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 1 1 1 2 2 2 3 3 3 3.
Uneventful? That's good. Thank you very much. However, there is an elephant in this room, and he's on the screen. This algorithm is n squared, or m times n, but the two inputs are the same length, so we don't care. It's n squared. If you have audio, in this case at 48 kilohertz sample rate for 1 minute, let's say you're using 32-bit floats, and you pack the direction arrows down into 2 bits for like none, match, insert, delete. Yeah, that'll work. Then you end up using 35 terabytes of RAM. And so you could go out to disk, right? But my NAS isn't that big. And also, I don't have all of my life to wait for that 17-second clip. So we're going to make assumptions about our data. We love making assumptions about our data because life gets a lot easier that way. We're working with the human voice, and the recording is at 48 kilohertz sample rate. That puts Nyquist at, we're in Sweden, let's do it right, Nyquist, at 24 kilohertz sample rate. So for those that are unaware, Nyquist is a principle that you need 2 sample points to record an oscillation. You need up and down, which means that the highest frequency you can store is at half your sample rate. The human voice isn't all that interesting above like 6K. It's mostly noise and like that kind of thing. The tone and the formants and the why is lower than that. So we can easily take that down by 4x. So we end up with Nyquist at 6 kilohertz. That should be safe. If it's 4 samples off in the alignment, that doesn't really matter because of our later stages. We'll talk about that later. So that moves us down. If we're at 12 kilohertz sample rate for 60 seconds, that gives us about 2.2 terabytes. Still not quite there. So another assumption we can make is that we have our actor with the lavalier, me holding the boom. Suddenly, the picture is really big, so I can't get close with the boom. But there's never really going to be a situation where the time difference of arrival is going to be any larger than like 20 meters worth of time. So we can just take the 20 meters at the speed of sound. That's about 0.58 seconds. 0.058 seconds. At 12 kilohertz, that's around 700 samples, which is nothing. So if you look at our cost map again, and we just take the range of 1,400 samples. It has to be double of 700, so you can warp both ways. Like the microphone can be, like one mic can be 20 meters further away than the other, or the other way around. So you need both sides. And we could just cut away all the other stuff. Now, in the literature, I later found out that this is called a Skjegstad band. In keeping with like technology people loving complicated names to make stuff sound really cool. But I have a way cooler name because when we came up with this, I was in a Discord call with Ginger Bill. And so in my code base and in my head, this is a Bill band. Okay? And that's what it's called from now. I'm renaming it. And doing this brings us down to 4.28 gigabytes. That's pretty good. Now I can run that. I don't want to, because I have other processes running, and Chrome is in the background, so I don't have that much, right? So there's another super easy, low-hanging fruit thing we can do, because when we're moving this wavefront up, here you can see I've cut away the stuff we don't need. We only really care about the current floats and the previous row. So you don't need to store all the other stuff. That gets us down to 0.5 or 0.25 gigabytes. That's doable. I can deal with that. But that's still for 60 seconds. And so there's going to be some instances where you have really long files and you need to warp the whole thing and align it. And what you can do in that case, you can just do a calculation up to some certain limit you've set of RAM use. I call these crystals because they kind of look like crystals. This is probably not a novel technique, but I've been calling it crystal DTW because complicated names make it sound really cool. If you just calculate that, it's going to be wrong at the end, but the beginning and the middle are going to be right. So what you can do is just calculate another one from a little bit further back. That one's going to be wrong at the beginning and the end, because if you remember, the algorithm always assumes you want to go to the exact corners, which is not going to be correct. However, there's a section in the middle there where there's overlap. These are not to scale. When you limit to like 1,400 samples, it's a really long and skinny crystal. So there's going to be convergence between the two when you overlap them. So you do same thing here. That's going to be wrong at the beginning. But then in the end, if you just swap at the overlap points, you get a correct path in the end. And that way you can do arbitrary lengths. Spectral phase, though, is going to come and kind of throw a wrench in our thing, because you can have things that are kind of in like timing, but we'll see here. So I'm assuming everyone here is familiar with FFT or the Fourier transform. Some people just know it as FFT because we never use the slow FFT. But that lets you go from time domain into frequency domain, and everyone knows it tells you the amplitude of each frequency. But at least in the sound world, it's not commonly known that it actually gives you 2 numbers per frequency, because it's a complex number, which no one in audio knows what it means. I'm insulting myself in the past there, by the way. Don't, like, audio people, don't come at, I'm insulting myself. I didn't know until I started looking into this. It gives you 2 numbers. It gives you the amplitude and the phase of each frequency. And if you're comparing 2 tracks, you can have a mismatch in just the frequencies of so like the phase of individual frequencies. And this will cause cancellation just at those frequencies, even though it's basically in time. So we can have a listen, if this will load. Yeah.
Hello. This is a recording of me speaking to you outside on a beautiful Swedish summer day. Now I have started messing with the spectral phase of this signal, and you probably can't tell. However, when I start mixing the original and the signal that has been messed with, you will notice that there's something very wrong with how this sounds.
Those 2 files, that's one file that's just been duplicated. They're basically in time. The only difference is the spectral phase. And so when you have 2 things, it's 180 degrees off. The waves will cancel at specific frequencies. And the way we're going to fix this, it's very complicated. We're going to do mem copy. And I've found that basically works. There's some implementation details to this, but this is essentially what I'm doing. It's just overwrite the thing and then have a blast. So let's listen to what kind of results this will yield. Graciously, I've been given permission to use some recordings I did on a shoot a couple of years ago with a man named Richard, an English gentleman and a scholar with a very warm and nice voice, which will work very well for demonstrating how the boom sounds okay, but you want even more of that warmth. You add the lavalier, and you lose it. So first you're going to hear just the boom. You'll hear it with the lavalier and with the lavalier that's been warped.
The first place to look for installing solar panels are the places that require the least amount of materials and the least amount of land use change, for example, rooftop solar. The first place to look for installing solar panels are the places that require the least amount of materials and the least amount of land use change, for example, rooftop solar.
That's a very easy test case because he's not moving all that much. He was leaning a little bit. And we're indoors, there's no noise. So here's a more difficult case where we were outdoors in the Norwegian midwinter and stepping through like crunchy snow, where there was a tiny path between some solar panels. And Richard was walking towards us, the camera guy was backing up, and I was behind the camera guy trying to like not step outside the path and make noise in the loud snow. Of course, Richard stepped in the snow, and you'll hear that. So this is an example of how this algorithm will handle noise around the place. Because you might think, what if it starts aligning with the noise from his shoes or something, and then like jumps back and forth, similar to how it mismatched the cycles.
One of the amazing things about solar parks and solar panels is that they're modular, so it's very easy to scale them up to much larger capacities. So we can study a pilot system like this, and then with the information that we learn from that, we can then scale it up to much wider systems, delivering much more renewable electricity. One of the amazing things about solar parks and solar panels is that they're modular, so it's very easy to scale them up to much larger capacities. So we can study a pilot system like this, and then with the information that we learn from that, we can then scale it up to much wider systems, delivering much more renewable electricity.
There we go. Thank you. Thanks, guys. I want to thank my friends Sam, Philip, Charlie, who helped me a lot in the beginning of this. Bill also, and Andrew. And also big shout out to, I hope I get this right, Martin, for being a very helpful signal processing god who just suddenly appeared in our Discord after I was stuck on a signal processing problem for a week. And like, I'd never seen him before. I didn't know he was in there. He just showed up and like, oh, by the way, I have a PhD in signal processing. And like, yeah. So that was cool. Everyone go check out silvernode.io. He's working on a really cool photo editor that's fast and doesn't suck. So yeah, that's me. I was gonna try and remember your fun username, but I cannot remember it now, and I apologize. But yes, we're gonna go to Q&A.
With Jack Brown.
Jack Brown was the real name, yes, thank you.
Ready?
I'm ready.
Cool. So first off, thank you for this conference. Thanks, Sam. Thanks, Charlie. I think everyone here will agree that you've done an incredible job with the production. And
thank you.
Yeah, another round of applause for Sandra.
Thank you. Thank you.
So first thing I want to ask is, I've known a few audio engineers being in music production circles myself.
Yep.
Not many of them go towards computer engineering or software engineering. So what brought you into that world?
Okay, I'm gonna reveal my soul a little bit here. Anguish and a thirst for revenge. I grew up having acquired Adobe software around the age of like 10 or 11, and I learned to make movies with my friends, and it was the best thing ever. And then over time, I watched all of my beloved creative software get more and more trash and charge more and more money every month from my pocket. And when I went into the industry, gradually, I can't, like, I need the software now. So now they're just siphoning money for software I hate every month. And I figured, you know what? I have to start doing something about this. So I want to, at least in the bit of the creative world where I live, I want to try and make it less shit. Yeah, so that's part of it.
It's very on theme for the conference, so
Yeah.
makes sense. Okay, so you mentioned that when you were talking about the time warping algorithm, there was a neat trick that you did on a special number that you were not so interested in, but
Yeah.
I think people would be curious to hear about that.
Right. The neat trick is that you can run the algorithm on the waveforms twice. You can do it one time with both waveforms the same way, and then you can invert one of them. And then you compare the number at the end between the two runs. And the one that gives you the lowest number means that probably you should just invert the polarity of one of the signals to make the warping less costly. And this generally means this is an automatic way to see if, classic example, you record the snare drum from above and below. You have to flip the phase of the bottom one, otherwise you'd ruin the sound. And this is just something you have to know. But that will tell you that automatically, and then also run the dynamic time warping, which is neat.
Yes, that is a neat trick. So nice. Cool. So this one's more of a personal question. When mixing music, myself and a lot of other producers commonly get ear fatigue, which is where you become blind to offensive sounds, you become blind to sort of intrusive frequencies. Is this something that you find impacts your ability to debug code like this, audio code, or is it something that kind of you're not listening so much that it doesn't become a problem?
This is so when you're working with phase stuff like this, and you're listening really close for is this going a little bit for hours? You hear everywhere afterward. It doesn't matter how clean the output is. You think it's there. And what I noticed is in the testing 1, 2, 3, testing 1, 2, 3 thing, is that I'm actually doing it over my desk. And so me moving the mic here is kind of creating two inputs to this microphone, the direct input and the reflected from my desk. And the two don't have the same distance. So there's a super minor bit of comb filtering happening from the fact that it's bouncing off my desk. And I started hearing that. I'm like, it's not working. I can't get this algorithm to work. I'm screwed. What am I going to do for the conference? So yes, it's a massive problem. But taking a stroll in the forest and asking the muses for help is useful.
Nice. Yeah, that makes a lot of sense. So you mentioned that the fast Fourier transform, obviously, which is something that's very fundamental to audio processing and any digital signal processing. You mentioned that was kind of implemented and that there was a neat trick with memcopy as well. And you said it was quite simple, but you didn't go into it. So I'm curious about if there's anything more you can do to expand on that.
Right. So when you implement FFT processing, FFT only, when you actually do FFT, you're doing it on a certain set of samples. But audio people think of it as like a real-time thing that plays, and you see the waveform move. And the way that works is you're doing tiny windows of FFT. And so you have an FFT window size. When you grab out a bit of audio, you move it to frequency domain. If you then mess with the phase and you turn it back, you can have situations where something, like you have a window here, you have a window here. You mess with the phase of this one of the waves is now going, and it ends further down. And in the next window, you mess with the phase, and that starts here now. And so in between each window, you get a click. So you have to apply a windowing function, which is basically you just fade out the in and the out of the little window. You do this on output as well, very important, so that you fade out any phase bullshit you've done. And then you can overlap the windows. In this case, I had to do it 75% overlapping to get rid of the clicking that would happen in between each window. And those windows are really short, so it ends up sounding like. But so that's most of the implementation detail there. And it's kind of, I should have maybe included some slides of it, but it's kind of fascinating when you see the before and after of doing the FFT overwrite, because it's almost like it just, because of the downsample, you can be a few samples, a tiny bit of samples off. You do the FFT overwrite, the phase overwrite, and it goes, it just snaps into place in a really satisfying way. So those are the slight details on that. I'm still tuning it because there's a bunch of different windowing functions with different trade-offs. Right now I'm just doing a sine wave. It's okay, but I think you can still get it more lossless. Yeah.
Yeah. Okay, that makes sense. I have 2 more questions before opening up to the audience. I suppose if people are interested in this sort of audio programming, now a lot of people here do probably audio program for games and software, but in the creative space, is there any way you might suggest people go to sort of look more into it? Because I myself have looked into it, and there's not a whole lot of resource for things like music production in software and sort of film and audio.
Ooh, yeah. It's a wide field. If you're doing music, it's very genre specific. I think I find a lot of rock producers go purely off of vibe, and it works great for them. They don't need to know the technology. I pan hard left and hard right, and that's the only thing I ever do. That one's a little too loud, you know, and it works great. But if you want to do like crazy producer porn, neuro sound design stuff, then YouTube is the place. For audio programming, there's actually very few resources. I don't think I've actually seen anything in specific. Luckily, it's just like arrays of floats. So it's not like you really need that much info if you know some programming. The one tutorial that I read and super appreciated was Next has a tutorial on how to use or set up a clap plugin, which I'm very grateful for because I love that clap exists and is the beginning of the end for VST, which is a mess. Dude, everything's a mess. It's crazy. Yeah, those are probably the. Yeah, Seamless R. He's cool. He does just good sound design stuff and goes into some wave theory things. And yeah, I think it's just years of messing around in audio software. Yeah.
Okay, sweet. And my last question for you. So you've given a talk on a very interesting topic. As a general overview, I guess in terms of either a wish list or just what you can see in general, as a quite untouched field, do you see where either you're going to go next in terms of solving problems with audio, or yeah, just in general, where you think the problems need to be solved in audio, software side?
I think this has frustrated me for a little bit, and this is very relevant. This is not going to be things, this is going to hopefully stop being relevant in a few years. But currently there's a big revolution happening with recorders being able to record in 32-bit float audio. And this has been marketed to beginners as a thing where like, you don't have to set the gain anymore because it can't clip. Because you record in 24-bit integer, it can hit a roof. Like you go to 0 decibels, full scale, and then it just clips, it goes distorted. Whereas float, when you're storing it as a float and you have 2 separate DACs with different whatever, basically it lets you go above 1 and just store a float value. And so it can clip as much as you want, you can just recover the peaks in post. And that's really useful. The thing that it does is that it solves clipping in a good way. Because it means that any dynamics that went beyond what you thought you could record, you can just recover and it's fine. The current solution in the most common industry paradigm is that you have a limiter before your DAC and stuff, so that when you're nearing that 0 dBFS roof, it starts to curve it off. It reduces the volume a little bit. And that way, it doesn't distort, but you lose the dynamics. And in our case, in the film world, that's really important because that's the dynamics is like the performance, man. It's the art, you know, the actor yells a little bit extra or decides to laugh loud and interrupt the thing in a specific way, and you don't want to lose that. And there's been a lot of resistance to it. Lots of software still doesn't somehow support float, which is like, I don't know how you don't support float. It's the goof. Almost all audio software internally works with 64-bit floats. And like, you will hear it all the time, even from audio professionals. Oh, but then we have to convert the workflow. And like, it's gonna be so much work if it's 32-bit float instead of 24-bit integer. which is like converting from 24-bit integer in some arbitrary scale thing is harder than going from 32-bit float to 64-bit float. So this has been like super annoying to me. That needs to be solved. There's still pipelines where you edit the film, you export the timeline for the sound guy to start working on the audio mix, and it will chop off 32-bit float audio that's clipping. And like the whole point of recording in 32-bit float is gone because it's just distorted in post. When you get it as a sound guy, like, oh, fuck, you know. Now I have to find the email for the sound guy that originally recorded it and ask him for the original files in case he hasn't formatted his drive or his SD cards. So that needs to be fixed, and I'm going to complain about it.
I'm extremely glad that question kicked off a passion rant. That was exactly what I was looking to do. Okay,
Cheers.
Question from the audience? Wasim?
So this is coming from a non-audio guy. I have no idea about any of this. So I'm just wondering, while looking at this, it seems like a pretty significant problem, actually. Like, you can hear it, even for a non-trained ear.
Yeah.
How does the film industry even try to solve this? Or, like, is this solution completely new? Is this something already researched? How is this approach usually?
So the old way was literally you would insert warp points, and I've done this for hours. You insert warp points, and then you sit stretching it to align it. And if you have the spectral phase issue, which is very common because on the lavalier track, you'll often put a high pass filter to remove any like low frequency rumble and stuff. And in order to make a high pass filter that doesn't have a delay or pre-ringing, you're gonna mess with the phase. So that was a pain in the ass. There's apparently one plugin that can do dynamic time warping, but it's very expensive and forces you to use iLock, which, you nodding? Yeah.
I hate it.
Dude. So iLock is this DRM dongle that takes up a USB port on your computer. Like, I just will not use this. I will not pay $300 for you to waste a USB port on my computer. There's apparently one. I haven't tried to use it, and I couldn't find any resources about this when I tried to search for this stuff. This might be the first time that this has been presented, at least this method. I don't know if that's what they use, but.
Either way, it's the first time for the bill band.
Yeah, man, the bill band, it's goated.
I was a little bit curious to hear about like the way you implemented this, like what language and what interface did you do, but also like how much is your USB dongle going to be for your implementation?
It's going to be $500. Yeah.
How much of that is going to bill for the bill brand?
He will get paid in me rewriting it in Odin. I wrote it in C++, largely because I wanted to make it as a clap plugin initially, and that's a C system. And I just didn't want to try and figure out, because you have to export as a DLL and like link with shit. It seemed complicated to try and do it from a different language, even though I do really like Odin. At this point, kind of regret not writing it in Odin and just trying to figure that out, because I probably would have learned something and it would have been a lot easier. I also learned a lot in the process, because initially I was writing it very C++-y from my bit of time in the university, having taken object-oriented classes in C++ and like, to use the STD. I was STD counting all over the code base. STD count, alligator, stdendl. Bro, stdendl has pain. And then Sam, luckily, came in and was like, why are you not just printfing? There is printf. And also, why you have pragma once everywhere? Why are you including everything everywhere? And it was, so I've turned gradually into like from C++ to C++. And those are the implementation details. Yeah.
You're very much hammering home Eskil's point about this being like an AA meeting for object-oriented service. You're like, I had to see out everywhere, man. I couldn't do it.
Yeah,
I see them in my dreams. Okay, next question. In the middle.
Yeah, so you have like doing a commercial release. You said it's a plugin, but then you like release it and sell to people. How can I what should I tell my audio friends about it? Because like I wanted to tell about your thing, but
Yeah.
like, should I tell you should buy this plugin, like you should buy this program, what it's gonna be, and when. And
Yeah.
amazing talk, by the way.
Thank you. I am working on a plugin, but it's figuring this out. Really, like that was the easy first 90%. And as we have now learned, the hardest part is the last 90%, where you have to deal with other people's code and like put it in a plugin, and have to deal with like what the plugin just gets live audio in. It can't see the audio files that are in the project. So you can't just like give me the audio buffer, I'll do stuff. You have to like, okay, when it's playing, then I capture stuff. What's the current time when I get this? Write my own buffer, and then like capture that. And then I was like, wait, what if they pause? And then it moves back. Okay, so I have to have a thing where like if it pauses and it stops, and the buffer that I just got input is like half empty because they paused halfway through a buffer. There's just like so much shit you have to think about when there's other people's code and you have to integrate it into a system. So the plugin took way longer than figuring this out. Eventually, I hope to have a plugin. First, though, I'm going to release some program where you can just drag and drop a file in, and it does it and spits out a copy of the file that's been warped. Because I don't see a reason, really, to have it as a plugin that's running all the time and spending CPU and RAM.
And where people can subscribe for the news, because you didn't promote like a social media, like how can you follow? Do you have Substack?
Oh yeah, I should have prepared for this. Yeah, you can go to sparkbursts.net. That's where it will be eventually. I don't have a newsletter or anything. I really should have prepared for success, as they say. But no, you can set sparkburst.net as your homepage, and you'll see it eventually.
All right.
So in the film or audio industries broadly, it seems like a pattern that there's a lot of these, like you were talking about hand editing the split points, like going through the entire audio file and doing a lot of manual labor, like slowly iterating through the entire window.
Yeah.
I don't think, I've done a little bit of video editing myself, so like correct me if I'm wrong, but it seems like there's more of this type of problem. Like it seems like there's lots of things that either video editors or audio editors do that that requires like a ton of manual like sweeping over everything. And I know to some degree that'll always be required. But I wanted to ask your opinion about like what are the other problems where you find either video or audio editors are spending most of their time in software, most of their manual energy in software. Because I feel, you know, I'm curious about your ideas about like where the biggest bang for buck is in automating more of that kind of ridiculous manual labor like this did.
Right. Yeah. So a lot of it is spent, when you do it properly, a lot of it is spent like just leveling, making things even, make sure the environments feel about the same in the different scenes, that kind of thing. And there are some plugins that will like try and level out automatically. The issue is that they are all largely in the same paradigm of getting live input. So when you skip around, they get confused, or they have to reset or something. There are extensions out now called ARA, Audio Random Access, where they will get to see the buffers in the thing, but it's not everything uses that, and it's because it's largely in VST. I think they're working on it for clap, but nothing supports it for clap yet. You still, like, if you're going to do it properly, you're going to be sitting there leveling a lot of shit. And plenty of time is spent cleaning up other people's mistakes on set. That's also an insult for myself, sound people. People have to clean up my mistakes too. But it's a lot of just like, oh, there's like a bit here where there's crackle from wireless issues. And then you have to know that you open this file in RX, and there's a specific type of noise removal that works very well for that one. And you just have an aesthetic sense that kind of noise removal will work for this problem. And you do that through a whole 1.5 hour movie on every single clip. And that's like a massive bulk of the work, at least when you're doing dialogue editing and that kind of thing. And I don't know how you'd automate it. That's the issue. Because like there's plenty of things to just do like, oh, AI noise removal, and it sounds trash. You can't just toss it on, because either it doesn't remove the weird noise you had with a plastic bag, or it removes too much.
Yeah, there's so much artistic, like you need the mind there to automate that kind of stuff.
Yeah, the director wants his mind in it. Yeah.
Any more questions? Oh, tell.
Small follow-up is, do you feel like if we solved half the problem, you could detect those cases and queue them up as like a priority list that you just kind of click through, and then you listen to it, figure out what to do with it? Do you think that would go a long way, or is most of the time actually the fixing and it's pretty easy to scrub through, right?
It's pretty easy to scrub through. I personally just keep, you can have a time, you can have like a marker for a point in the audio program. I start that at the beginning of the film, and I just move it as I work through it. And then I'll do that once, and that'll be like my pass-through of noise removal, and I'll just move it back and do it one more time to make sure I didn't miss anything. And usually after that, it's fine. So the queuing up isn't too hard, and I'd be afraid of false positives, where you have a scene where someone's eating and you actually want some of the fork noise or whatever.
See, any more? No. Okay, one more on.
I have a question, which is, yesterday the stream went amazingly well, and we have all the VODs. And today, well, hold on, I don't want to scare anybody. Today we have all the data for the VODs, but there was a slight outage on the stream.
Yeah.
Why was that? Why?
It's because I bought this like shitty $4,000 laptop, and thought this will be great for running like streams. And then we did for one day. Day 2, blue screen before we even begin. I'm like, wow, thank goodness that happened before we started streaming. Foreshadowing. And then it's blue screened like 4 times during the stream, and we've had to replace it with a Mac, because Macs are like alien technology that haven't added that blue screen feature yet. So this seems to be working, just running OBS. But the streaming program we were using, Touch Designer, which I love, can only encode video for live streams with NVENC. So you can't use it on Mac, because there's no NVIDIA graphics card in it to do NVENC. So you just get an error saying, I hit the live button, it goes red. I check Twitch, offline. I go in, look at the node for streaming, little red guy. No, sir, no NVENC. So now we're using OBS, and it's like a backup thing, sadly. Technology doesn't work.
You can record to a file.
You could record to a file. The file works because you can do QuickTime encoding to animation codec, but Twitch doesn't support that.
That's great.
And also, they didn't have a software encoder for H.265 or H.264 for some reason. So
Should have bought an $8,000 laptop.
that's the trick. I should have bought a Mac. Yeah.
Okay.
But there isn't a more expensive Mac. This is like a consistent problem. It's like you cannot spend more money to get a better machine.
This is true. You cannot just turn up money and get more out, because like it actually, wherever you put it, it's gonna suck.
So does this mean we need to make better software?
This means we need to make better software. That's right. That's right. Yes.
I might even pay $4,000.
Yes, I will pay. Yeah. Bounty. On Serenum, yes. If you do it on Serenum, I will pay $4,000. I will actually pay that if you do it on Serenum. At 1080p 60, though.
You need a cluster, right?
Yes. Yes, spend $4,000 first on Serenums, and then put them in a grid.
Like a rack, we do like rack servers and like.
Yes, sir.
Okay. Any final questions? Oh, okay, one more 100 applause for Sander.
Thank you. Thank you. Thank you, brother.